I'm going to take a slight tangent from my last videos. Although still related, I'm going to leave my Arduino project and look at a similar project using a Raspberry Pi. In this video, I'm going to explain about how to control addressable RGB LEDs on a Raspberry Pi so that it can be controlled from a web browser, mobile phone, or used in home automation. Previously, I explained how to control WS281x pixels, also known as NeoPixels, wirelessly using an Arduino Nano RP2040. I'm going to continue creating some more videos on that project soon. I've just got the PCBs back from the manufacturer, so hopefully I'll be including that in my next video. But in the meantime, I thought it would be useful to look at implementing a similar interface for a Raspberry Pi. This will provide an alternative to my NeoPixel GUI program I was using before. I had already created a graphical user interface application for a Raspberry Pi, which I used to provide lighting sequences. This was originally intended for using NeoPixels for disco lighting. I then added addressable LEDs outside my house, which can be used to light up the handrail which goes up my driveway. So far I've been using the same GUI application to control these, but whilst this is useful if you want to control them manually, it doesn't allow for automatic lighting control. The key part of this is that instead of having a graphical interface running on the Raspberry Pi, instead it is provided through a web server running on the Raspberry Pi, which can be accessed through any web browser on that computer, on another computer, or even a smartphone. It also provides a way that this can be controlled through home automation using crontab and wget. This is what I have, which is a Raspberry Pi with a level shifter located in a waterproof box outside my house. The Raspberry Pi connects to my home network so that it can be accessed by other devices. There is a simple level shifter included in the box, which then connects to a Pixelstrip installed under a wooden handrail. I've used a simple inverting MOSFET level shifter, which is adequate for this job. See the description for a link to more details about this. The first decision was the language to program this in. I would normally choose Python, as that is the language I use the most, and so I'm more familiar with it. But in this case, I was porting an application that I'd written in C++ on an Arduino. Ideally, I wanted to be able to keep the sequences in sync, so I thought it would be easier if I wrote the code in C++ on the Raspberry Pi as well. I did a significant amount of development in C++ using the Boost ASIO library, but I realised that it was taking a long time to develop and was turning into hundreds of lines of code. I also realised that the sequences files that I was hoping to use would need a significant amount of rewriting anyway, because of the differences between how C++ works on the Arduino and on the Raspberry Pi. So that took that benefit away. I therefore decided to switch to Python using the Flask web framework. I've not used Flask before, but it's very similar to Python Bottle, which I have. Within less than a day, I managed to create all the code in Python for the main server application, and it was just a case of porting the sequences across. So I found that using Python was actually much easier than using C++. In addition to the server code, this also needs a bit of HTML, JavaScript, and some CSS. Those are all identical to the Arduino versions, and it was just a case of copying the original files onto the Raspberry Pi. I'm going to go to a little explanation about how the server works before I go on to showing how you can create your own custom sequences and use it in home automation. If you're more interested in those parts, you can skip forward to the next chapter. The Flask web framework provides a way of serving web pages using Python. It can be called from a separate web server, such as Apache, but in this case I'm using it in the development mode, which uses a built-in server. They recommend against using the Flask server in production environments, but this is only a simple application and it's more than capable of what I'm doing with it. But the option is there to move it onto a more suitable web application if you want to. In addition to the web server component, there needs to be a way to control the pixels. This is achieved through the Raspberry Pi Python WS281x library. The library is easy to use, and I've created tutorials on that already, See the link in the description. The main aspect of this code is that I've incorporated multi-threading so that Flask, which is handling the incoming web requests, and the updating of the NeoPixels is handled simultaneously, or at least neither one is stopped waiting on the other for any significant time. I've created two threads. MT is known as the main thread, as it handles the updating of the pixel strips, and FT is the Flask thread. The main process is actually still active, but it's no longer tasked with anything other than waiting for the other two threads to complete. Note that these are different threads rather than processes. The distinction is that whilst threads are allocated memory for their own use, they can still access the memory of the parent process. This means that information can be shared between them using global variables. The Flask thread is responsible for updating two variables. The seq set variable is a dictionary which holds the information for the web server about which sequences to run. The uptime variable is then updated with the time that the variable was last updated. These variables are only updated by one thread, which is the Flask thread, and read by the other thread, which is the main thread. This means that I don't have to use mutexes to lock the variables, which would be required if both threads updated the same data. Here is the code which is opened in the Thonny Python editor. Start with the file pixelserver.py. This is the main program file. And if we scroll to the bottom of this, you can see here that this is the code for starting the threads. We have the MT, the main thread, and FT, the Flask thread. And these are both started here as when it's executed as the main program. Now scroll up, this is the main thread. This is relatively short here, and this is used to update the pixels. This is where the global variables are accessed, the two variables here, and it sets up some local variables. Also pulls in the configuration file from pixel config, we'll cover that later. The sequences from pixelseq, again we'll look at those later, and then just sets a couple more variables that those will actually be updated later, but they just need an initial value. Then the code calls this while loop, and this is where all the updates to the pixel strips are made. This while loop does use a time.sleep at the end, which is based on the delay that's set for that particular sequence. This does mean that there will be a pause or a delay between commands being changed and them actually taking effect, which will be determined by this sleep value and how long is remaining on this. Using the web interface that's been created, this won't be more than a second anyway, but it's just something to be aware of. It shouldn't really cause any problems. And then the rest of the code, really just reading in the global variables and then passing them to the update seek method, which runs the appropriate sequence. Then the other part is the Flask thread. This is fairly straightforward. It just launches the development server here from this thread. But the way this really works is using these at app.root Python decorator methods. And these just handle the particular request from the web server and then call the appropriate code. For instance, slash would return the index.html file. Similar thing with CSS, returning the appropriate file, and the .js file. The /sequences.json file, or request, returns a list of the sequences that are available formatted using JSON format. That's all handled within the sequence list, which is in the pixel sequence file. But the most significant one is the /set method. This is quite a bit longer because it includes some additional security checks that I've added since porting it from the Arduino version. This is important to validate the inputs to ensure that the commands sent from the web browser are valid. With the Arduino version, because there's no operating system as such, there was limited exposure as to what you could do if you were able to cause a security overflow or anything like that. However, with this Raspberry Pi version, we've got a full operating system, and you wouldn't want somebody being able to cause, say, a similar buffer overflow and then being able to access information that they shouldn't that's related to the server. Note, this doesn't mean that this is a secure server and that you can just put it out on the internet. There's no authentication at the moment, so if you did, then you would allow anyone to control your LEDs. But it just provides a bit of error checking before it passes that along. So I recommend you only connect this to a secure network, but it does at least have some of that checking. So after it's checked all the values are valid or as expected, it updates these global variables here. First adds the values that it's been storing in this temporary new values dict and copies those into the seq set dict, or makes that equal to them. And then it updates the time with the current time, and that's just a timestamp so that the main thread knows that that variable has been updated, it's time to read it again. There's a separate class to handle the configuration, and that's saved in pixelconfig.py. And this uses a default configuration file called defaults.cfg, which has got all the default settings for the pixel strips. And you shouldn't edit this file directly. Instead, if you want to overwrite any of these values, you just copy that particular line, or in fact the whole file, into another file called pixelserver.cfg. For instance, in this one you can see that I've increased the LED count to 150. Set LED invert to true, that's because it's used in an inverting buffer. And I've set the maximum brightness of the LEDs to 100. You'll notice that the list of config, these are the only config options available at the moment. This is quite limited, and it's only limited to configuration of the pixel strips. The other things that you may want to change, for instance, relate to the IP address and port of the server. These are not included in the configuration file. Instead, if you're looking to deploy this on a different port or to make other configurations to the server, then you may want to look at hosting the site through a web server, say something like Apache, rather than using this development server, as that will potentially give more functionality through that. And then the other file is this pixelseq, it stands for pixelsequence.py file. And this contains two classes, both of which need to be updated if you want to add a new sequence. I'll go through these one at a time. The first one is the seq list file. And the main part of this is a list of sequences with things like their name, title. And this is used by the web page, particularly the web server, to know what buttons are available, and this is also what's going to create the .json format file that I referred to earlier. This is also used by the random function. So if you wanted to have a random sequence displayed, it will look at that list that's up here, and it's got some colours that could be used by the random sequence. The other class that's in here is called Pixelseek, and this is the code that is going to make the sequences that run. Also needs all the methods that you're going to add into this sequence methods dict, and this is used to define the methods that are used to correspond with the buttons on the web server. This is similar to how I used function pointers when I created the Arduino version, and you can think of this as substituting the particular dictionary element with the respective method, which is handled through the update sequence method, which is here. And really this just is a way of taking the request from the Pixelserver.py and making it run the appropriate method. And then this is followed by all the methods used for the sequences. These are mostly a direct port from the C++ version, and they use the same library, being the Pixelstrip library, so the formatting of these is very similar. And there's very few dependencies, so it actually makes it quite easy to port across by just taking the instructions in C++, changing the syntax or the way that it's entered, and just putting it into here. But I have made some improvements on some of these, and I've made a few other changes which I'll explain. So if you just look at one of these, we can have a look at the arguments that need to be passed to it. And these are similar to the way the Arduino version works, but there's one less parameter. So the first one is the sequence position. This is a number indicating how far in the sequence this is. It's used a way of remembering the state without having to use class variables. The reverse option is a boolean, which reverses the direction. How this works depends upon the sequences. For instance, for all on, it changes the ordering of the colour sequence. For a chaser, then it changes the direction that the chase will go. So if it goes from left to right, it will change it to right to left, or vice versa. And then the final argument is colours, which is a list of the colours to use. This will always have at least one colour, the default being just one white colour. Note there's no need to pass the number of elements in the list, as this can be easily determined from the Python list using the len function, whereas on the Arduino version we did pass that separately. There are a few changes I made to the way that the sequences are defined, and this is to add additional functionality, and these changes will be ported back to the Arduino version as well in future. One is that all the sequences must run for a set period of time and must always return seq position value of 0 when that period is over. So in the cases of these functions or these methods that are static, they don't really need to track this sequence position. To support this, they do. And in the case of all off, it just counts up till it reaches 10 and then goes back to 0. All on, I've set it a bit longer. It goes up to 20 before it goes back to 0. I'm still experimenting these to get values that work best, but that's the general principle. And then the same with the flash. Before that would only go 1 and 0, but that means you'll only get a single flash if you're using the random method, which we'll call this. So I've set that so this counts up to 20 and it flashes based on odd and even numbers using modulo 2 as a comparison. I've ported some of the methods over, but I'm still working on some of the others at the moment. But I have added one new one, which I'll show, which is this random sequence. This, as its name suggests, will choose a sequence at random. And it does that by using the list of sequences and choosing one of those, making sure it doesn't choose itself, because obviously that would cause random to be causing random, and we don't want that. If you set the colours, then it will maintain those colours and it will use those colours on all the sequences that random chooses. Or you can just leave it as the default, in which case it will choose 4 random colours for each sequence, and it will change those each time it chooses a new sequence. If you wanted it to be just white, which is normally the default, but obviously the default is replaced with the random colours, then you can just choose 2 white LEDs and then it will just keep white in the sequence. You can run the program manually. If you change to the directory pixel-server and then sudo to run as root pixelserver.py. You need to run as root both for the web server, because we're running on port 80, which can only be used by the root user, and also for the access to the NeoPixels. There's a little warning about using the development server, but we don't need to worry about that. Then all you need to do is open a web browser with the same IP address as your server. If you're running this directly on the Raspberry Pi using the built-in Chromium browser, then you can just put 127.0.0.1, which refers to the local address. But I'm accessing it from another computer. This is from my Linux laptop, and I've just entered that manually. If we look at the server, you can see the pages that it gets. So when you start, it downloads the standard HTML, CSS, JavaScript, and the sequences, which is used to create the buttons that are available. So on the website, you can choose one of the sequences. There's only a few on here at the moment. I'll be adding more later. So you say choose the flash or the chaser sequence. You can set the speed. Note that this is in terms of delay. So if you move it to the right to the end, you'll get a delay of 0. Now, in reality, that would be far too fast to run, so you probably don't want to go quite to the end. And if you go all the way to the left, that's 1,000 milliseconds, so there's 1 second between each sequence. You perhaps want somewhere around the middle for a reasonable speed. And then you choose the colours that you want. If you leave it with a single white, that's the default. Or you can say select these. You choose the black, that will mean the the LED is not lit, it's left off. And then you click apply, and you'll see the sequence start, and you'll see a message on the screen with this sequence. Now this is useful potentially later if you want to use this for using in automation to make this sequence start automatically. This is quite responsive when accessed from a different computer. But if you're running this on a Pi Zero and trying to use the browser that's built in, then you will find that it's quite slow. There's some things that we can look into later about the reason for this, but it's usually better to interface this from a more powerful computer, or if you're using a Raspberry Pi 4, that would do that. One other thing is the reverse option is there, which is just a toggle button. And the important thing to remember about this is that whatever you change, nothing actually happens until you click the apply button. So this allows you to set up what your next sequence is going to be. So you can, for instance, if you want to change to a different sequence, then you can set that up ready, change the sequence and the speed, and none of this is taking effect until you click apply, and then it all takes effect at the same time. I'm now going to have a look at the performance of the Raspberry Pi running the Pixelserver and see what we can do to get reasonable performance out of it. So I've switched now to, this is my actual outdoor lights, and this has got it set up as a server daemon. I've just rebooted, and the only thing I've launched is a terminal session and the browser. So I'm going to pull up, I'm going to use the local address 127.0.0.1, that means the home computer, and this is going to take a short while to load, and see that this is perhaps a little frustrating. But this is specifically running on a Raspberry Pi Zero and running a graphical interface over VNC, and then running the web browser on there. But of course you don't need to do this. You can run the web browser from any computer. You don't have to run it on the actual machine itself. So now that's started, we can have a look at the performance of this. I'm going to use HTOP, which will show us the top processors in terms of using resources. You can see it's showing the one we're using the most CPU resource at the moment. It's actually the VNC server. But just to have a look at the Pixelserver, I'm going to hit F4 to filter, and I'm just going to type Pixelserver, and you can see there's 3 processors running here. So this is launched from systemd. You can see the top one here, PID 390, is the process that systemd started, and then after that it spawned 2 more processors, or they appear to be processors, they're actually threads, and this is just a way of that HTOP displays them. One is for the Flask server, which is the web server, and the other is actually updating the pixels. It's not actually running at the moment, so you see that CPU usage is negligible, between 0.6 and 1.2. Memory usage is very low. So if we just start this with the default one, if I just go put the flash one on and click apply, and we can have a look at see the resources now. Again, the CPU is still very low and memory is very low. You can see that this is the one that the thread that is actually running the pixels, because it's the one that's using some of the CPU usage, whereas the other one's negligible, and that's just because it's just running the Flask. So we can see what happens if we increase this, and we are good if we go all the way to the fastest setting. So this has got a delay of 0. This is going to be running flat out as fast as it can. I still use the flash, it doesn't matter which one I choose. And we'll see that there's a significant increase in the amount of CPU usage. So just hit 42%, hovering generally around the 30s. So it's using 30% of the utilization of a Pi 0. Now, in fact, you wouldn't run that speed. That is incredibly fast and it's just a blur. So if we turn it down, I'm going to give a delay of 36 milliseconds. This is still incredibly fast. But we can have a look and see how that affects the performance. So straight away you see it's down to around about 14% utilization, and that's really not very much at all. You'll see that it looks like we're running twice as much here, but actually it's not. This is a cumulative total of the processors of the individual threads. And if we drop it down a little bit further to something that's a more reasonable speed, around 100 milliseconds, this is still a tenth of a second, so there's 10 changes per second, and then we get it down to a much more manageable number of, say, less than 7% CPU. You'll see that the memory usage has barely changed throughout these. So now if I remove the filter, we'll see what's really going on this Raspberry Pi, because you'll see most of the time it's almost 100% utilization and a lot of the memory is used up. So if I just clear this, and it's quite clear to see that the things that are really taking up the utilization, we've got the Chromium browser here. There's a lot of processors or threads used by the browser. In fact, I'll just turn that off. I'll just take off the browser as well. And you'll see that with the browser gone, CPU utilization is still quite high, but a lot of it is going to be due to the graphical interface, the fact that we're running a graphical interface. You'll see things like OpenBox, you'll see the LX sessions, you'll see the LX panel, which is the panel up here, and you'll also see the VNC server. Between those, they are going to be taking up an awful lot of resources. So now I've finished developing this, or I've got another machine I can develop on and then just push to this. Really, I can just turn off VNC and turn off the graphical interface, do it all through the Raspberry Pi configuration, and just run it as a headless machine. I wasn't able to do this before because I needed the graphical interface on this to control the lights, but the reasons for creating this is so it's just going to be a basic server application running on the Raspberry Pi, and then to access it, to change the sequences, you would of course go to a web browser, which could be on a PC or on your mobile phone, and you'll see that the performance of that is much better. If you do want to control the pixels directly from a graphical interface on the Raspberry Pi, then I suggest you use the faster model of the Raspberry Pi to make it more responsive. A Raspberry Pi 4 would be able to handle this using the Chromium browser and the Pixelserver code without even breaking a sweat, and you'd be able to use it for more things as well. So there's an option if you want to be able to run it directly on the Raspberry Pi with this interface. So the last thing is to set this up as a server and have it run automatically. I've actually already done it on here. I can show you how this is set up. So inside the code there's a Pixelserver.service file, and that needs to be copied into the /etc/systemd/system directory, and you'll see it here as Pixelserver.service. And then you can enable that using the systemctl. So use the start to start it, status will give you the status, and enable will actually enable it to automatically start. Just do status and the Pixelserver.service, and this will give you the status of it running. And I'll just show you the .service file. This is the file that actually does that. Just got description. It's saying to start it after the SSHD service has started. Gives it the working directory, command to run. If it fails, it will automatically restart it, run as a root user, and the wanted by multi-user.target means that it will start during the startup process before the setup is complete. And then to be able to have this automatically, you just need to have something that tries to retrieve a web page. I use the wget command. You may need to install that using sudo apt install wget. But wget basically allows you to pull down a web page. So here's some examples when I've been doing some of the testing. So wget, show the command, wget -o redirects the output. Here I've redirected it to a file, but when I use it in automation, I'll just ignore that file by rerouting it to /dev/null. And then the web page you want to get, HTTP. I'm running it on the local machine, so I've used 127.0.0.1. If I was running this on a different machine, because I could run this from any Linux computer, then you would put the IP address of this server on there, and then the command that you want to run. And that can be placed into the crontab using crontab -c. Let's see, I've got two commands here. One that will turn it off. I'll just make my terminal a bit bigger to make it easier to get all in one line. So the second line's still being wrapped around, but the first one. 0 minutes, 22 hours, so every 10 o'clock every day of the month, every month, and every day of the week, run wget, and it's this command here, which will turn it off. And then at 4 o'clock on any day of the month between October and December and January and March, so only over the winter months, day of the week, Monday to Friday. So this will bring these lights on when my children are coming home from school, 4 o'clock in the evening during the winter when it's getting dark. And there's the command to turn them on. You can put any sequence you want here. If you want to see what sequences are, you can go to the log, and if you run the command you want through the web page, it'll then end up in the syslog. So you can grep server syslog. And you can see when I've been doing the testing, these are the commands that have been run. So you can just copy and paste that, prefix it with, well, from there to there, prefix it with http:// and there you go. This is now usable as it is, but I'm planning to develop this a bit further. At the moment I'm looking at adding more in the sequences that I've added to my other versions of my NeoPixel software. I think it's likely I'll cease further development on the NeoPixel GUI application, which I'd created previously, just for the reason that this does everything that that did and more. I had started looking at how I could turn the NeoPixel GUI application into a client-server architecture, but really that's not necessary, as this provides that function with a simple to use interface. I'll leave the code up on GitHub for the GUI application. You can continue to use it, or if someone did want to fork that, they can do so, but I'd rather spend the time developing this newer version. And thanks for watching the video. In the next video I hope to go back to the Arduino RP2040 and give an update on the electronics side of that project, controlling NeoPixels in the same way but using the Arduino. If you like this video, please give it a like, and if you're not yet subscribed, please subscribe to get future updates. I look forward to seeing you in my next video.